Hi everyone, welcome back to the course on measurement and instrumentation, and this is the 7th week of our discussion and we are talking about transducers, and this is basically the third module of our course. Today is the 5th lecture in this particular week, and today we are going to learn about new kind of transducer that are used for the measurement of temperature. Okay. We know that temperature is one of the most commonly measured physical quantities across all the industries as well as in our day-to-day life. Okay. The measurement of temperature is essential for industry process control, for power plants, chemical processing, electronics and biomedical system. If I point to exact utilization, but in general it has usability even beyond this. Okay, even smaller plants, even smaller factories will require very accurate temperature sensors for their day-to-day operation. Okay, temperatures are measured by any temperature transducer. Mostly you have two type of transducers, either you have a contact type or you have a non-contact type. Okay. In the contact type, we have various ways of measurements, like we can use thermocouples, then you have RTDs, thermistors and so on. Okay. In the non-contact type, mostly they are optical devices based on infrared or some radiation pyrometers are also used. Okay. In this course, mostly across the today's lecture and in the next lecture, we will try to understand mostly the contact type of temperature sensors. Okay. If you see any temperature sensor, the desired characteristic or from the user point of view are several, like you want any other sensor or a transducer, you want it to be highly sensitive, you want to respond very fast to any change in the temperature. Okay. Accuracy also is something which is desired by the end user. Okay. Then stability of the device over certain temperature range, particularly in the temperature range where the user want to operate this temperature sensing devices, the performance should be stable. Okay. Then repeatability is another thing which you want over the temperature range. Okay. And then wide temperature range is something which is required. All right. So the contact type devices are mostly based on resistive principle. So let us learn about resistive thermometers. Okay. The resistance of a conductor changes when the temperature is changed, and this property is exactly what is utilized for the measurement of temperature. Okay. The advantage of this kind of devices are they are very simple. Okay. And when they are simple, means that their interfacing circuits are also not very complex. Okay. And their sensitivity and stability are also very good. Okay. So these resistive thermometers can be of different type, like you have RTDs, PN junction detectors and thermistors. Okay. They can measure temperatures that are referenced to an absolute temperature scale, so we also call it absolute sensor or transducer. Okay. The variation of resistance R with temperature T can be represented by the following relationship for most of the metals, as you will see that in the RTDs we mostly utilize certain kind of metals. Okay. So the resistance variation can be written as R is equal to R naught, where R naught is the resistance at temperature 0. Okay. So R is equal to R naught into 1 plus alpha 1t plus alpha 2t square and so on, depending on how many terms are dominating in this equation. Mostly higher orders are neglected, but this is the generic equation where alpha 1, alpha 2 and till alpha n all are the constants. Okay. So in this series, let's try to learn first the RTDs, which are the resistance temperature detectors, and these are a very crucial device from the industry point of view, particularly if you talk about measurement and instrumentation. These RTDs dominate the temperature market for the industry perspective. Okay. Now this RTD, this particular term is usually very common for metal based devices. Okay. So these metal based devices are either fabricated in the form of thin wires, okay, or they are also sometimes formed in the form of thin films. Okay. Nowadays, this class of temperature sensors also cover some semiconducting materials with pronounced sensitivity to any temperature variation. Okay, like we have devices based on silicon, based on germanium, and so on. Okay. The RTD devices are, as I have mentioned, you can obtain wire-based devices as well as thin film devices, and both have their own applications. Okay. Now, temperature dependence of resistivities of all metals and most of the alloys gives you opportunity to use these metallic materials or alloys in temperature sensing. Okay. While all metals can be employed for sensing, platinum is used almost exclusively because of the various properties, including the predictable response, long-term stability, and durability. When I say predictable response, means that from its transfer function, you can actually derive response in the higher temperature region as well as in the lower temperature regions. Okay. Tungsten RTDs do exist, but they are mostly applicable for anything higher than 600 degrees Celsius. Below 600 degrees Celsius, mostly you rely upon platinum based devices. Okay. All RTDs have positive temperature of coefficient because all these are metallic material. Okay. So several type of them are available from various manufacturers. You can have a look on different industries which are in this business. You will find that a number of companies are competing to sell their RTDs. Okay. The resistivity of metals showed a marked dependence on temperature, and this was exactly discovered by Sir Humphrey Davy, and that's how the RTDs had started. But only the change in the resistivity of metals was discovered, but it was not being used until Sir William Siemens started using platinum for resistance thermometer, and his choice actually proved to be most suitable, and till now we use platinum for high accuracy resistance measurements across the industries. Okay. So as I have mentioned that these RTDs are available in both the kind. You have thin film RTDs and you have wire based RTDs. So thin film RTDs are mostly fabricated of thin platinum or its alloys and deposited on a suitable substrate, like you can have a micro machined silicon membranes, you can also have it on mica and so on. Okay. And if you see this structure, it looks like a kind of serpentine, you can see that it is zigzag on this substrate. Okay. This is made in this structure mostly to ensure a sufficiently large length to width ratio. So if you see, the length is too large as compared to the width, and this gives you better efficiency. Okay. So this kind of deposition is can be done by various ways. You have you can use concept of shadow mask. Okay. So shadow mask is a technique that is used across microelectronic laboratory, at least, to deposit this kind of complex structure using certain hard mask. Okay. So basically what you have is, and this is more dominant when your structure are in certain millimeter or at least hundreds of micrometer. So exactly like if you want to deposit this, so you have a mask made like this, like serpentine. Okay. And I'm just giving you a hint. Okay. And like in the thermal evaporator, for example, if you know, there are various methods of deposition of these materials. You have PVDs and you have CVDs, physical vapor deposition and chemical vapor deposition. Usually physical vapor deposition is preferred method for depositing these materials. In fact, in microelectronics also people use physical vapor deposition to deposit metals for making contacts and for different interconnect applications. Okay. Now if you have this kind of shadow mask, please note that this area is hollow. Okay. And this is say part of a bigger say aluminum sheet or a stainless steel sheet. Okay. Now in the deposition system you have a wafer kept like this. Okay. And in between you have this shadow mask, patterned shadow mask, right. and below you have this crucible in which you are evaporating say aluminum or say nickel for making this serpentine nature thing, okay. And by just evaporating and using this, you will have exactly the pattern transferred on your wafer. Okay, this is a very crude technique for deposition, but more scientifically proven techniques are like in the form of certain lithography. You have photolithography in place to fabricate this kind of devices. There also you should have a hard mask, and there we use a concept of photoresist. Okay, photoresist are the materials which changes its chemical properties when it is subjected to UV lights. Okay, so you say, for example, say I have a silicon wafer, okay, on which say I want to pattern this thin layer of platinum. Okay, so I have a silicon wafer, all right. On top of this, I coat certain photoresist, okay, and then I subject it to UV light. Say this is a UV light, okay, through a mask. This is the hard mask, okay, made up of say chromium on glass or something like this, okay, chromium on glass, right. And then you expose it. Depending on it is positive photoresist or negative photoresist, it will be either soluble, it becomes soluble in certain solvent, or it become hardened, you know. And when I am saying that this becomes soften and harden, you know, I am talking about the area which are exposed to UV light, and the other, if this area is softened, means that other area is hardened, and vice versa, okay. And accordingly you can develop it, we call it development stage, and you develop it, and then you will have this transfer of pattern from this particular mask to this photoresist. And once this transfer is done, means that you have already got a temporary pattern on your wafer, okay. And then by different techniques, by etching or by lift off, you know, you can pattern the platinum thin film layer like a RTD, all right. So usually this is the more conventional and more scientific way to pattern these thin films of platinum, okay. Then we have wire wound RTDs, where the platinum windings is partially supported by a high temperature glass adhesive inside a ceramic tube, something like this. So here you can see that you have this ceramic bobbin, and these are the leads, and this wire is on this wounded inside this high temperature glass substrate, okay. Now this construction provides detector with the most stability for industry and scientific applications, because these are the rugged devices, and their industry actually utilizes these devices regularly, okay. Now the requirement of a conductor materials to be used in RTDs, there are various qualities that you want in a metallic material or in an alloy material for being suitable for the RTD application. You cannot utilize any material for the RTD, okay. The first requirement is the change in the resistance of material per unit change in the temperature should be as large as possible, okay. This is desired to have better sensitivity and better response, okay. The material should have a high value of resistivity, so that a minimum volume of material is used for the construction of the RTD. And the third requirement is the resistance of the materials should have a continuous and stable relationship with the temperature, so that its transfer function at least can be predicted, okay. Now gold and silver are rarely used for the construction of RTDs on account of their low resistivities, because we have just seen the three qualities that you require for material to qualify as RTD material, okay. Tungsten has relatively high resistivity, but is reserved for high temperature application, as it is extremely brittle and difficult to work, and we have just seen that anything above 600 degrees Celsius are handled by tungsten based RTDs, okay. And then below is mostly handled by the platinum ones, okay. Copper is again used occasionally as an RTD element, but mostly it is avoided, okay. And the most common RTDs are made up of either platinum or using nickel, or sometimes some alloys of nickel. Okay. The economical nickel wires are used over a limited temperature range, and industry knows that exactly in what temperature range they will be working on, and accordingly they choose among them. Okay, either they can go with this nickel or nickel alloy or any platinum based devices. Okay, these devices, the nickel alloy and others, they are quite non-linear and tend to drift with time. So for measurement integrity, only you have one choice, that is platinum. Okay, and that's how industry has mostly accepted the platinum resistance thermometers for these applications. Okay, you can see some of the characteristics of resistance thermometers based on nickel, copper and platinum as shown over here over a large temperature range. Okay, an examination of this resistance versus temperature curves show that the curves are nearly linear, and if not completely linear, then also in certain temperature range it is linear. Okay, so when you consider a short temperature spans, at least they have better linearity, or linearity becomes more evident. Okay, this fact is employed to develop approximate analytical equations for resistance versus temperature for a particular metal. Okay, and you will get several equations for RTDs. Okay, however, the one that we have seen will be following that particular thing, because that is more generic equation. Okay, but depending on the model and the material you may have, and of course the temperature range, you may have more accurate equations. Okay, then once we understood this metal based devices, because as I have mentioned that RTDs are mostly dominated by this metallic materials for the development of temperature sensing devices. However, silicon has also gained certain popularity because they are more kind of CMOS compatible, and it gives you opportunity to integrate with the existing devices. Okay, so pure silicon, you talk about either polysilicon or single crystal silicon. Okay, intrinsically they have negative temperature coefficient of resistance because they are semiconducting materials, and we know that inherently the metals have positive temperature coefficient and the semiconductors are the NTC devices, or they have negative temperature coefficient of resistance. Okay, however, you can vary that by changing the doping concentration. Okay, so when it is doped with an n-type impurity in a certain temperature range, its temperature coefficient become positive, as you can see on the graph also. Okay, so this is the result of the fall in charge carrier mobility at lower temperature. Okay, however, again at higher temperature things changes, and the number of free carrier increases due to the number of spontaneously generated charge carriers, and the intrinsic semiconducting properties of silicon again start to dominate. It means that you have a window of temperature in which you can utilize this highly n-doped silicon material for RTD, because we have seen that RTDs are PTC devices or positive temperature coefficient devices. So in the range or in the regime where silicon or doped silicon possess, you say, positive temperature coefficient of resistance, in that particular range I can utilize them for the as a RTD device. Okay, so at temperature below 200 degrees Celsius, the resistivity rho has a PTC for the silicon, while over 200 degrees Celsius it becomes again negative. So around 150 to 175 you can utilize it as a RTD device. Okay, so based on this you have KTY sensors in the market. So the basic KTY sensors consist of a N-type silicon cell having approximate dimensions of around 400 to 500 cross 500 cross 240 micron. Okay, metallized on one side and having contact areas on the other side. Okay. Now, this kind of structure produces an effect of resistance spreading, which causes a conical current distribution through the crystal, significantly reducing the sensor's dependence on the manufacturing tolerances. And KTY sensors may be somewhat sensitive to a current direction, and especially at larger currents and higher temperatures, and this is one of the issues with KTY sensors. So to tackle this problem, a serially opposite designed are employed, where two of these KTY sensors are connected with opposite polarities to form a dual sensor to avoid any kind of direction dependent on the current. Okay. Now these sensors are especially useful for the automotive application, and that's how they exist, particularly when the temperature range of operation is less than 200 degrees Celsius. Okay. So a typical sensitivity of a PTC silicon sensor is of the order of 0.7% per degree Celsius, that is its resistance changes by 0.7% per every degree Celsius, and this is a typical curve for in the temperature range of say -50 to 150 for a KTY sensors. Okay. As for any other sensor with the mild non-linearity, the KTY sensor transfer function may be approximately given by the second order polynomial as shown over here. RT is equal to R naught into 1 plus A T minus T naught plus B T minus T naught square, and I am not having the other terminologies to make it more relevant. Okay. In this case again R naught and T naught are the resistance and temperature at a reference point. Okay. Now RTDs comes with various advantages. Okay. They have high accuracy, we have seen for platinum devices. Okay. They have very good stability because mostly they are metallic materials and there is very less chance of any breakage. Okay. Now they have very good repeatability over a wide temperature range, and they have mostly the linear characteristic, and even if it is non-linearity, you can use piecewise linear approximation to approximate the linearity in particular temperature regime. Okay. However, they comes with also various disadvantages, like they are costly because you are using a metallic thin film or very costly metallic thin film actually, and then metallic wires. So it's not that you are using metals like platinum just to make contacts. What you are using it, your complete device is made up of platinum. So cost is something which you have to bear with. They are also poorer in response, particularly if you compare it with the existing devices based on say thermocouples. Okay. And they have limited temperature range. We have devices which can of course handle beyond the temperature of 600 or so, but then it cannot measure anything less than 600, right? So both of device, maybe platinum and tungsten, they have their own merits and demerits, but mostly they have limited temperature range. Okay. Similarly, the KTY semiconductor temperature detectors, they have high linearity, and this is one of the advantage, although there is a mild non-linearity that we have seen. Okay. And they have very good accuracy and stability, and they have a wide operating temperature range, anything from -50 degrees Celsius to around 150 degrees Celsius or even little higher than that. Okay. Now they have good sensitivity, rugged and reliable in nature. Okay. They have low self heating errors compared to other devices that we will talk about. Okay. And they have the facility of interchangeability, means that devices, when they have high tolerance, replacement does not require recalibration in many of the time, and this is the device where interchangeability is something which comes as the added advantage. Okay. Then we have different disadvantages also for KTY temperature sensors, that like if you see, although I am telling that -50 degrees Celsius to 150 degrees Celsius is a wide temperature range, but maybe the user may be requiring temperature range say -100 degrees Celsius to 400 degrees Celsius or so. So if you see that kind of thing, you have to rely upon the existing RTDs based on metallic wires like platinum or so. KTY sensors may not be suitable for that kind of application. Okay. Also they have lower accuracy than platinum RTDs, and they also require calibration for precision work. Okay. So even you have to do calibration regularly if you are using it for very highly accurate or highly precision kind of work. Okay. Although non-linearity is not very prominent, but then also we have seen that performance is moderately non-linear or mildly non-linear. Okay. And last but not least, it has lower sensitivity than NTC thermistors. Okay. So we have not discussed the NTC thermistors, but maybe in the next class we will start our discussion on NTC thermistors. So NTC thermistors provide a large resistance change per degree as compared to this kind of devices, and therefore it's very important to learn about this category of devices also. Okay, so maybe in the next class we will continue our discussion on temperature sensors, and we will talk about the thermistors in the next class. Thank you.